We will define the entropy change ds for a small part of the process, during which the system and the surroundings exchange reversibly a small amount of heat dq reversible at the temperature T. Note that ds is a change in the extent of disorder in the system and arises from the exchange of heat with the surrounding during the process. A positive value of ds implies that the system entropy increases, which is consistent with a positive heat dq being transferred from the surroundings to the system. Conversely, a negative value of ds implies that the system entropy decreases, which is consistent with heat, negative dq, being transferred from the system to the surroundings. Note also that the definition of entropy implies that ds must be calculated for a reversible path. Finally, note that ds is inversely proportional to the temperature. This is a subtle point, but a very important one. Indeed, one should expect that transferring a given amount of heat from the surroundings into the system can give rise to a smaller or larger increase in disorder depending on the actual temperature of the system. Dumping heat into a system at high temperature will indeed create much less disorder than doing so at low temperature. This is so because systems are typically more disordered at high temperature than at low temperature. If you transfer heat into a system that is already very disordered, you should not see a large change in disorder. If, on the other hand, you transfer heat in a system that is very ordered, you will significantly increase the level of disorder in that system. Looking at the definition of the entropy S, we expect the entropy to be an extensive function with units of joule per Kelvin. As for all extensive properties, we can define a molar property, here called the molar entropy, with units of joule per Kelvin per mole. Like the energy U and the enthalpy H, the entropy S is a state function. That is, the entropy S depends on the state of the system and not how we arrived at that state. The entropy change delta S for a process is obtained by integrating ds over a reversible path between the initial state of the process and the final state of the process. However, because the entropy is a state function, the entropy change delta S is independent of the path. This is a very important consideration that we will need to remember when we calculate delta S for processes that are irreversible. That is, for processes for which we cannot a priori calculate the entropy change directly through the actual path. Let us now look at the implications of what we just learned regarding the entropy and consider a process that transforms a system from an initial state I to a final state F. The entropy is a state function, so the entropy of the system, which we call Si, has a well-defined value, and similarly the entropy for the final state SF has also a very well-defined value. We a priori may not know whether the actual process is reversible, spontaneous, or not spontaneous, as this is often the question we are trying to address. So we cannot calculate the entropy change by following the actual process. On the previous slide, we learned that we can write an equation for ds for processes that are reversible. So if we want to calculate delta S, we need to consider a reversible path between the system's actual initial state, I, and the system's actual final state, F. If that is what we need to do, this is what we will do. We will imagine a reversible path that starts in the same state I as the actual path and ends up in the same state F as the actual path. The change in entropy for the system for the actual path is delta S equals SF minus Si, and is the same as for the imaginary path because the entropy is a state function. As this is a very important statement, let me say it in a slightly different way to make sure this is as clear as possible. The change in entropy, delta S, has a value SF minus Si that is independent of the path chosen because the entropy is a state function. So to calculate delta S, we always choose an imaginary reversible path because we have equations that describe the change in entropy for a variety of simple reversible processes. These equations will be described in more detail over the next 3 slides. Calculation of delta S for the surroundings are much simpler because surroundings are so large that transfer of heat into or out of the surroundings does not change their temperature, and the process of heat exchange with the surroundings can be considered to be reversible. So we can write the change in entropy for the surroundings as Q surroundings divided by T surroundings, the temperature in the surroundings. We learned in chapter 1 that energy is neither created nor destroyed. What this really means is that the heat that enters the system comes from the surroundings and vice versa. Practically speaking, Q surroundings equals minus Q system. So to calculate the change in entropy of the surroundings, we simply divide minus the heat associated with the actual process for the system by the absolute temperature in the surrounding. So to summarize, to calculate delta S, that is the change in the entropy for the system, we need to imagine a reversible path and calculate the entropy change along that reversible path. On the other hand, to calculate delta S surroundings, we simply divide minus the heat for the actual process by the temperature of the surroundings.